previous classes, from previous lessons, we looked into the chapter content from all the way here, and I think we came pretty much to this point, writing electron configurations, and all the way to writing condensed electron configurations. So we are going to pick things from there. But I just want to highlight that if you examine previous exam papers, you will see that you're frequently getting questions from these parts in recent years. If you check starting from 2017, 18, 19, 20, and 2021, every year you had at least one question, not that part, I was highlighting the wrong part, from the quantum numbers. So this part. Pretty much every year you had some sort of a question from that part. So make sure you know how to figure out the quantum numbers. Sometimes those questions are combined with electron configurations. So make sure you know it, because it is a very easy point to take, and it is also very easy to forget this concept by the time you're done with all the 14 chapters, all the 14 units. It's very easy to forget even the names of these quantum numbers. So make sure you know these things until very end, because those are just easy points. Now we'll start from where we stopped. So last time we looked into building the electron configuration. We looked into the Aufbau principle, where you are filling electrons from the lowest energy orbital. You fill the electrons from the lowest level, and you follow the Hund's rule and the Pauli exclusion principle when you're filling these things. And things go smoothly until 3p. It fills up in the order you see as 1s, 2s in the principal quantum number level. But after 3p, you know that what fails is 2s, and after that, 3d. So just to recall what we did last time, this is your Aufbau principle, the filling order. You have to memorize, or at least understand how to fill this electron correctly. And talking about the exceptions, chromium is one such exception that you can expect an electron configuration like this one. It's not 4D. So 3D 4. 4s2. You expect that kind of a configuration, but you actually get an electron configuration like 3d5, 4s1. And we've looked into this concept, why this happened, if you consider the expected setup. These are the 3D orbitals, and here I'm showing the 4s orbital. And when you fill the electrons, according to the expected configuration, it would look like this. But thinking about the actual configuration, it's going to look like this. So here you see a precise half-filled situation. And these precise half-filled situations are unusually stable. They have some stability. And that is why they go for this kind of a deviation from the Aufbau principle. And make sure when you fill the electrons and write the electron configuration. Now I have written, if you check the filling order, you can see after 3p, what fills is 4s. So if you think about the filling order, let's just think of chromium because that is what I'm talking about. You have the argon configuration. First, you fill the 3Ds, sorry, the 4s. You first fill 4s, so it is 4s1, 3d5. That is the filling order, but our writing order is this. So you have to order them in the increasing order of principal quantum numbers. So make sure you know that this writing order is going to be helpful in a later step. We are going to talk about ion formation, writing electron configurations for ion. So if you write it in the filling order and try to figure out which electron is going to walk out first, you might have a little problem figuring that out. That is why it is important that we practice to use writing it in this order, not exactly in the filling order. All right. So we were looking at some exception, and if you can recall, another exception we talked about was copper. And you can see that copper is here, and our previous example, chromium, there. Now in the copper as well, you would expect argon 3d9, 4s2, but our actual is a 3d10, 4s1. And if you consider this electron setup, you can see that these d orbitals have been completely filled. This one is completely filled. And the 4s is half filled. So this situation brings more stability than the one you expect. So that is why we have these kind of small deviations from the Aufbau principle. It is seeking for stability. Complete filled orbitals or half-filled orbitals are going to be more stable. And the reason why chemical reactions occur is because of this stability. The chemical reactions occur seeking stability. So everything pretty much want to be stable. Now let's see what we can do for the next element. Now we were looking at this period, And you have to practice writing electron configuration actually all the way to atomic number 54. So from hydrogen to xenon, you should be able to write electron configurations. How do you write it? Follow this filling order. You find few exceptions. One here, another one here. Now, if you think about zinc, now our copper electron configuration was argon 3d10 4s1. Then what should we get for zinc? It should be argon 3d10 and 4s2. Now we can keep on going writing electron configurations. Next element is gallium. Let's write electron configuration for gallium. The expanded electron configuration can be written as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p1. And you can see I have written these things in the filling order. Try to recognize what your noble gas structure is. Now this set is going to be argon electron configuration. See where gallium is in the periodic table and where argon is in the periodic table. Now you can see you get the core electron configuration or the inner gas structure from the inert gas just above the period where you have your element. Gallium is in the period 4, and the noble gas structure you're using is directly above that. So you're always using the noble gas that is in the previous row, not in the same row. In the same row, you have krypton. You don't use that. The noble gas structure you use is the previous noble gas structure. And then I will write it up in the proper writing order as 3d10, 4s2, and 4p1. Now you can see what happened. We started filling the p orbitals. And where did we started filling it? Right after zinc. Right after zinc, we started filling the p orbitals. And if you do it for the next element, germanium, atomic number 32, you will find that it is going to end with 4p2. Arsenic. If you write for arsenic, it will end with 4p3. And it goes on 4p4, 5, and 4p6. So now you can see there is kind of a trend. Everything in this group end with a p1 configuration. Everything here with a p2. And then p3, p4, p5, p6. Now, helium is an exception. Helium, we don't have any p electrons or p orbitals. So we have an exception for helium. And previously, you may have noticed that things in the other end here, things like hydrogen, lithium, they ended with S1. Things like beryllium, magnesium, their configurations ended with S2. Now you can see there are certain patterns. Now, in your own time, make sure that you practice writing the electron configurations. Here I'm showing only up to 36, but make sure you know how to write electron configuration all the way up to atomic number 54. From this set I have shown, you have the exceptions at copper and chromium. All right, now let's go to the next period. Earlier, we were talking about the period number 4 or the row number 4. But now we are going to the row number 5 and see what kind of electron configurations and what kind of anomalies we will face. Now, what is the noble gas structure right before this group, this period? So that means in the period 4, we have krypton as our noble gas. So every element that we write in this period will have a krypton electron configuration as their core electrons. Krypton electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, and 4p6. So that is the krypton electron configuration. And if you're writing the electron configuration for rubidium, you're going to have a krypton core and you will have 5s1. Writing it for strontium, you will have krypton core and 5s2. And then the next one, which is yttrium, you have krypton, you have the 5s2. What fills after 5s2? This is where you have 5s. What is the next available level? So you're going to have 4d. Before you fill 5p, you can see p up here. So before you fill the 5p, you're going to fill the 4d orbitals. And that is all from the Aufbau principle. You fill the lowest energy orbitals first. Now, zirconium. We have our next element, zirconium. You can have the krypton electron configuration, and you can write as 5s2 42. So if you're writing in the filling order, oops. So in the filling order, you first fill the 5s, and then you had the 4d, but this is the filling order. And when you're writing in the other order, the proper writing order, write krypton as 4d1, 5s2, and this as 4d2, 5d2. This is our writing order. All right. Next element is niobium. If you're thinking of the same filling order, we would expect an electron configuration like this for niobium. But the issue is that is not the case. This is what we expect, but what we actually get is something like a 4. Let's see. What you get is a 4d4 and a 5s1. Now this is an exception that you will find in the period 5. In the previous column, we saw the exceptions in chromium and copper, but in the following period, we are going to find more than that. So why exactly is this going to have that kind of electron configuration? Why this have the electron configuration of 5s1 and a 4d4? Now, if you look into this configuration, now this is actual, and what we expected was in the expected version, this is the expected. But in the actual version, what we have is this. Comparing the actual and the expected, you can see that in the actual one, it is much more closer to getting half-filled situation. This one is actually half-filled. And the others, they're almost there. But in the expected one, it is not the case. I mentioned that when you have electron configuration, either the orbitals are completely filled or half filled, there is this stability. So we can attribute this for that stability. Let's keep moving with the other elements that we have here. So right now we look into niobium, and then we are going to the next element, which is molybdenum. In molybdenum, you will find the electron configuration as you have the krypton core, and you will have 45 5s1. You might expect something like this for molybdenum. Remember, for the previous element, niobium, we wrote the electron configuration as krypton 5s1 44. So if not, I will rearrange it in the other order. So this is what we expected for this element. So based on that, we might expect molybdenum to have a 44 5s2 because we have this 5s little bit lower than the 4d. But what actually happens is that there is a little deviation from the Aufbau principle. Draw the orbital diagrams. You will see the half-filled orbitals. And in the expected situation, in the actual situation, you will see this precise half-filled orbitals. But what we expected is something this. So this is the actual electron configuration. Why we have this exception? Because they are all precisely half-filled. And that result in more stability. But in the case of expected electron configuration, this is kind of a less stable electron arrangement. So keep in mind, it is very important that you understand this complete field and half field scenario and the type of exceptions you're going to see. And we'll look at the next element in the periodic table. You will have the electron configuration for this as a krypton core, and for the 5s2. Remember, for molybdenum, we previously wrote krypton for the 5s1. So now our krypton you can expect this one, and that is the actual electron configuration you're going to have. Next element is ruthenium. Now for ruthenium, you would expect something like this. Why? Because you have technetium with 4d5 and your s orbital is completely filled. So whatever the additional electron, you will expect to put it in the d orbital. So 4d6 and 5s2, that is what you would expect, but the actual is the krypton core. You will have 47 and 5s1. Now, you might find it very weird that it is happening like this, but again, you might see that there is kind of half-filled scenario here. So you can have the 5s orbital half-filled if there is this kind of arrangement. And I'm going to write another element right next to it, that is rhodium. You will expect a krypton core. You would expect 4d7, 5s2, but you actually get the krypton core 4d8, 5s1. Again, for simple argument, you can consider this also as half-filled, but the actual explanation can be much more deeper, and it goes into a deeper sense in the atomic structure that is not covered in the A-level syllabus. So even in the A-level syllabus, they are not pushing your understanding towards these three elements we just talked. So what are the three elements? The exceptions with this, ruthenium and rhodium. The syllabus does not strongly highlight these exceptions, but there is one element they want to see your understanding in terms of the exceptions in the Aufbau principle, and that would be palladium. So keep in mind, in terms of exceptions, you need to know from period 4 nor the exception for chromium, nor the exception for copper. And then make sure you know palladium very well. If you can work it out, you can keep in mind things like niobium, ruthenium, and rhodium, but what's mostly highlighted are these three elements. So let's look at palladium electron configuration. All right, based on the electron configurations we wrote previously, you might expect an electron configuration for palladium, something like this. So 4d8 and 5s2. That is what you would expect. And if you look into the orbital box diagram, your electrons will look like this. But what you're going to get actually for palladium is something like this, with a krypton core and 4d10. So now you're going to see that this 5s2, those two electrons are not in the 5s orbital. Instead, both of these electrons have been stuffed into the 4d orbital. So your orbital diagram would look something like this. If you want, you can put 5s, but your 5s is actually empty. So we don't write the empty ones. So see what happened. When it does this kind of a arrangement, this kind of a deviation, you can see this 4d orbital became completely filled. So that is going to give it some unusual stability. So in order to get that stability, palladium has this kind of an electron configuration. Now you might be wondering why elements do these kind of switches and why elements have this kind of electron configurations. The real reason is that, the real explanation is that this is all based on the experimental observations we have. So it is not like we build a rule and atoms working like that. No, that is not what's happening. The atoms and these elements, they're working in a certain way. And once we observe them, how they react, how they make ions, based on those observations, we built this Aufbau principle, the filling order, and also the exception. We had to make the exceptions because that is how those elements, those atoms behave. So basically what we do with these exceptions is we are providing an electron setup so that we can explain the chemical behavior of that particular element. So that is why we introduce these exceptions to explain what we have experimentally observed. All right. Now we wrote it all the way to Palladium, and I mentioned that you are supposed to know all the way to the atomic number 54. So what is the next element after Palladium? That is silver. So what is your electron configuration for this one, silver? You still have krypton as your noble gas in the previous period. You have krypton, and you have a 4d10 and a 5s1 electron configuration. The next element is cadmium. This will have cadmium. You can see that you can complete the 5s orbital. So cadmium will have 4d10 and 5s2 electron configuration. And similar to the previous row, start writing the electron configurations for indium, tin, antimony, and the rest of the element all the way to xenon. When you do that, you will find that indium configuration, you will have the inner electrons, the krypton core, and we just filled the 4d10 and 5s2 orbital, and indium will have the 5p1 configuration. As I mentioned, this is going to be p1, and see, we are on the period 5. So 5p1, and the next element tin, we are still in the 5th period. So in Sn, you will have krypton, 4d10, 5s2, 5p2. So this is p2. Antimony. We are in the 5th period. You will find p3. So for antimony, you will have all this structure as it is, and it will end as 5p3. This is going to be p4, p5, and finally xenon will end with 5p6. Now you see this S and P filling order. And you can see certain areas of the periodic table is going to have this p orbitals filling, and the other parts you have s orbitals filling, and certain other parts you will have d orbitals filling. So at this point, let me summarize what you are expected to know. So the things you are expected to know is that writing electron configurations up to 50, atomic number 54. The electron configurations up to atomic number 54. Know that. And then you have to know the completely filled and half filled electron configurations are more stable. completely filled, and half filled. Electron configurations. Stable than the other configurations. And that means things like S2. This is complete fill. And if you have a P6, that is complete fill. If you have a D10, that is complete fill. If you have things like S1 or P3, D5, these are half filled. So these type of configurations are going to bring in some sort of stability. And what else are you expected to know? You're expected to know the exceptions. The exceptions in 3D series. That is chromium, and the other one was copper. You would expect one type of a configuration, but chromium is aiming for half-filled orbital setup. But when it comes for copper, it's aiming for the 3D to be complete fill. And then you are supposed to know the other exceptions in 4D series. In the 3D series, what is important is chromium and copper. In the 3D series, what is more important is palladium. I know I mentioned few other elements like this, but their explanation, more sensible explanation, are beyond the scope of A-level concepts. So they would mostly focus on palladium rather than the other three exceptions in 4D series. So if you read the syllabus, you will find the same information that they are actually highlighting on palladium. Know the exception for palladium. Now, this is the filling order. You might think it is easier at this point, but sometimes students tend to forget this filling order as you advance with your syllabus. Now, ways, let's look at ways to memorize this filling order. One way to do it is through practice. Or if not, religiously practice. most of you, whatever the religion you have, you might have some sort of a prayer or something, but you always know, no matter where you are, what you're doing, if someone asks to say the prayers, you would know your prayers. Why? You have been doing it every day for your whole life. So you kind of have practice it. One way to memorize this order of filling. The filling order can be memorized practicing it frequently, including the exceptions. Another way you can memorize this is by building it yourself. Build this filling order by yourself, and I think I showed it last time. You can write this 1s, 2s, 3s, 4s in one column, and then all the 2p, 3p, 4p, like this in a pattern. You have 3Ds, the Ds and the Fs. And then you draw these kind of diagonal arrows, and then connect the heads and tails of these diagonal arrows, and then that will give you the filling order. If not, the other way to memorize this is through the understanding. You can figure it out from the periodic table. So how do you figure it out from the periodic table? You can see these numbers given as 1, 2, 3. They are the principal quantum number. And also, in the principal quantum number 1, you know you have only S. And since it is in the first level, it is 1s. And each orbital contains maximum 2 electrons. So hydrogen ends up being 1s1, helium becomes 1s2. Going to the next level, which is level 2, you know what kind of orbitals or the sublevels you have in principal quantum number 2. You have S and P. Since they are in the level 2, that is 2s and basically 2p orbitals. So you can see this ends with S1, S2, and then you start with P1, P2, and you can go on. The next level is the principal quantum number 3, where you have S, P, and D orbitals. Since you're in level 3, these are all 3s, 3p, 3d. The only thing is that you can see here you have an empty space. What does this empty space mean? That means you actually have 3D orbitals. You are in level 3. If you're in level 3, you should have S, P, and D, only that D orbitals are empty. So you have empty D orbitals when it comes for the third period. So when we write the electron configurations, now you go from 1s, 2s, 2p, 3s, 3p. You don't fill the 3Ds in these ones because they are basically empty. There's not enough electrons to fill that. And then going for the next period, you have again S, P, D, and F. And they are all 4s, 4p, 4d, 4f. Now, when you went on filling 1s, 2s, 2p, 3s, 3p, in the third period, your 3D is empty, you end up filling 4s, and then you start filling the 3D. See the pattern. You start from the S. These are the S ones. So this is 4s. These are 4s. 4s. And where do you have your 4p? This is where you have all the 4p electrons. Now you see your 3Ds, your D jumps in. This is where you have D. So you see that after S, before the P, in the level 4, you end up filling the D. So that is how you figure out from the periodic table how you fill these electrons. And next, what comes after 4p is this 5s. So by looking at the periodic table, you can also memorize the Aufbau filling order, what order you should be filling these electrons. All right, now let's actually walk into the periodic table. So when scientists were working on the atomic structure and doing a lot of experiments with electricity and radioactivity, they ended up discovering more and more elements. So they ended up discovering more elements, and once they had a reasonable amount, some scientists were trying to classify them based on their atomic masses. So two scientists who worked on this is Dimitri Mendeleev . He's a Russian scientist. And the other scientist was Lothar Meyer. He is from Germany. Now, both of these scientists around the same time, around the same year, published a paper classifying the elements that they already knew, and their publication were nearly identical, meaning that when in the scientific community, when we discover something, we publish our work, we publish our scientific findings in a journal. And it is very interesting that these two scientists in two different countries, they were not collaborating. They were independently working on their classification, and they ended up pretty much identical classification. And this is what their classification kind of look like. This is the old version of the periodic table. So how they classified is based on the atomic mass. They classified based on atomic mass. When they classified it based on the atomic mass, they came to know that the chemical and the physical properties occur periodically. So when they classified them in the increasing order of atomic mass, based on, I would say, increasing. Increasing order of atomic mass, that's how they classified. What they observed is that the chemical and physical properties occur periodically. What that means is that when you put them in the increasing order, the elements that show similar chemical and physical properties, he found them in one group. Things that show similar properties were in certain groups. That's what they observed. Somehow, this is not the current periodic table we use. We use something that is called as the modern periodic table. In the modern periodic table, we classify things in the increasing order of atomic number. So in the old version or the first version of this periodic table, they used the atomic mass, the increasing order of atomic mass. But now we are using the increasing order of the atomic number. This use. So this is what the modern periodic table is going to look like. And you can see the atomic numbers. They are all arranged in the increasing order. Now, when you read books or search internet, you may find many different types of periodic tables numbered in different ways. Let's try to understand some of those numberings. In some periodic tables, you will find this kind of Roman numbering with letter AB. And there will be some other types of periodic table. Instead of the Roman numbers, you will find the Arabic numbers as 1A, 2A, this is as 3B, sorry, 3A. And this one here as 3B, 4B. So all the Roman numbers as Arabic numbers. So that is another type of numbering system in the periodic table. Now, this was confusing different people in different regions using different numbering system, and sometimes it was confusing. What are we talking about? People don't know. So to resolve this confusion, the IUPAC, you will come across this name much more frequently when we go to the naming part. This is the International Union for Pure and Applied Chemistry. So IUPAC jumped in, and then they proposed a completely different type of numbering system. Instead of using this AB type classification, they started simply going with Arabic numbers 1, 2, and then we go on 3, 4, 5, 6, 7. This is 8. Oops, this one is 11, 12. Here it is, instead of 3, this is 13, 14, 15, 16, 17, and 18. So this is the IUPAC numbering system. So in the periodic table, whatever the numbering system you see, now you have an ability to correctly identify. What I have written here is a bit messy, so let me clear up certain numbers, mostly this part. So here you see in the Roman numbers 8A. If not, this is in some places, it is written as 8A. This is 7A, 6A, 5A. And in the IUPAC naming system, I wrote this one appearing as 13, 14, 15, 16, 17, and this one as 18. Do you see certain things kind of matching up? Here you see 3, even though it is 13, it still reflects something. So they are not just random things. So even if you learn things in the IUPAC numbering from 1 to 18, or the other numbering method from A 1 to 8, B 1 to 8, you can see that the numbers are perfectly lining up. So when we say group 3 or group 13, we are pretty much looking at the same thing. If you are saying group 4 or group 14, we are basically looking at the same group in the periodic table. So get used to this numbering system and be able to read the periodic table. All right. In the periodic table, I kept on mentioning a word as period. Periods are the rows. The rows you find across. And a while ago, I mentioned a name as group. These are groups or the columns. The columns are what we call as groups, and the rows are what we call as the periods. So that is some vocabulary associated with the periodic table. Now, let's see this periodic table in a little bit more details. The elements in the same group going to have same number of outer shell electrons. Elements in the same group related outer shell or the valence shell. Electrons. What I mean by that is if we take the group 1, I'm talking about this first group with the group number 1. if we take that and write the electron configurations, we will find that hydrogen has 1s1. And then if we take lithium, which is directly under hydrogen, has the electron configuration of helium core and the 2s1. Look at sodium. It will have this kind of electron configuration, and it keeps on going following a certain pattern. Now you can see they all end with S1. If not, I can say NS1 configuration. Only the principal quantum number change, but every configuration has this S1 part. And if we do a similar kind of writing for the group 2, we have in the second group beryllium. Right below it, we have magnesium, calcium, strontium, and it goes on. And if we write electron configurations for those, we will end up with this kind of a pattern. So they all end with S2. If not, I can write NS2 kind of a pattern. And think about group 13. Where is group 13? This is group 13. In some periodic table, with respect to some periodic table, you might even read it as 3A, but with IUPAC numbering, it's group 13. So in this group, you will find the elements boron, aluminum, gallium, like that, and you will see that the electron configurations end with helium, 2s2, 2p1, and for aluminum it's neon. It's going to be 3s2, 3p1, and for gallium, that is argon, that's 4s2, 4p1. So you can see all end with a p1. If not, I can write it as, to be more precise, it is ns2 n p1 nd. And as you go on, you will see that group 14, it will have ns2 np2 and so on, that kind of a pattern. Now going into this periodic table, this is where we had all the S1, S2, and starting here, we had P1, P2, P3, P4, and P5. Helium is a little exception. It has no P electrons. So it's P5, and this is P5, and this is P6. All right, so that means everything in this block keeps on filling the s orbitals. So here, s orbitals are being filled. So we call this block as the S block. And in this part, you see that the p orbitals are being filled. So we call them as the p block. So that means in somewhere in a text, it says S block elements. It's talking about things in the S block. And if it is referring to something as a P block element, that means it's talking about elements in this block. And we can do a little bit more naming, more like knowing your vocabulary. The group 1. This group 1 we call as the alkali metals. We call the first group as alkali metals. Know your exception. Hydrogen is not a metal. So even though I drew my arrow like that, I would mark hydrogen as an exception. This as an exception, everything else here is these are the alkali metals. You see that all the elements are metals. Lithium, sodium, potassium, rubidium, cesium, francium. They are all metals. And then the next group, which is group 2, we call them alkaline earth metals. Everything in this group. So the name says it, metals. They are all metals. And it says alkaline. Even in the group 1, it says alkali. What does that mean? If you put them into water, they will make alkaline solutions, basic solution. They make bases. At one point, you will be talking about acids and bases, strong acids, strong bases. These things in group 1 and group 2 metals, they make bases when they react with water, reflecting its chemical property in the name. Next set of groups we are going to look at. I'm going to start from this end, group 18, which is labeled as noble gases. And the name says it. They are noble gases. The gas, they are all gases. Things in this group is all gases. And then that's this group. Group 17. The noble gases, according to IUPAC system, we number it as number 70, the group 70. We call this group as the halogens. So what you have is basically things like fluorine, chlorine, bromine, iodine, like elements. And then the group before that, which contains elements like oxygen, sulfur, selenium. This group, which has IUPAC group number 60, is what we call as the chalcogenide or the chalcogens. They are the chalcogens. Now, these are some names, vocabulary that you need to get familiar with. If they say chalcogens, you need to know what they're talking about. Alkaline earth metals, you need to know which group number we are talking about. So those things, be familiar with the terms. There is another term that I want to introduce, which is called the representative elements or the main group elements. The representative elements, also known as main group elements. This is the S and P block collectively. S and P together, collectively called as the representative elements or the main group elements. Now there is, in addition to this S and P block, there are more blocks. Now we are going to look into that. There is something we call as the D block. D block or the transition metals. Now again, the word says it. Everything in this block are metals. You don't have any gases. You don't have any other things. They are all metals. So you don't have things like non-metals. If you think about something like carbon, carbon is a non-metal, but everything in this D block, they are all metals. And in the D block, you will see that you have 10 columns before the P block. So your P block starts from here. From there onwards, you have P. And if you consider the 10 columns before the P, that's what we call as the D block. So in the D block, the D electrons are filling. So this is where the D electrons are filled. So even though we say this block contain transition metals, things in the first transition metal column and the things in the 10th column are not actually considered as transition metals. Now, this might sound confusing. We say it's this D block or the transition metals, and then we are saying this the elements in the first column in the D block and the last column in the D block are not transition metals. So the transition metals, one way we can define it is that they lose electrons to form an ion with incomplete d orbital. Transition something. I think I kind of lost some of the writing by accidentally. Yeah, that was some sort of a error that occurred with my writing device. So I was working on the transition D block or the transition metal. But I mentioned that what you find here in the first group and the last group in the transition metal group are not transition metals. So what we define as a transition metal is something that loses electrons to form an ion with incomplete d subshell, incomplete d orbital. All right. So what that means is that the elements in this first column of D block, when they lose electrons, they don't have incomplete d orbital. So these guys, when they lose electrons, they do not form incomplete d orbitals. For example, you can see that scandium ends with the electron configuration D1. And there is only one d electron. And if scandium release this electron, it is going to end up as D0. So it's incomplete. There is no d electrons at all. So that is why it is not really considered as a transition metal. Then what is the matter with the other elements in the last column in this D block? The issue with these elements is that their d orbitals are completely filled. D block transition metals, they are supposed to fill the orbitals. And these guys have completely filled d orbitals. And when they lose electrons, they are actually not losing electrons from the d electrons. So since this is completely filled, see, it is completely filled. When something completely fills a certain orbital level, it becomes very stable. And because of that, it is not losing electrons. Not losing electrons from the orbitals. So because of that reason, we consider these elements in the last column in the D block also not as transition metals. Okay, so the transition metal, you might find a certain other boundary that we have here. So this lanthanum, these two elements are also part of D block. So these highlighted, blue highlighted parts can be actually considered as the D block. So what is up with the other ones here? So those ones can be called as the inner transition metals. You can see that two elements, two symbols, they have been kind of squeezed inside the D block. So the D block is transition, and something squeezed inside that is what we call as the inner transition. So in the inner transition series, in the periodic table, we end up separately showing these inner transition elements, which we call as the F block. So this is where F orbitals start filling. And for the A-level syllabus, we actually don't go all the way there. Remember, I mentioned this is how far we go in terms of electron configurations. But in general, you're required to know which block is which one, the SPDF blocks. So the if you this type of a representation of the periodic table, sometimes we call it as the long form. The other forms you saw like this are like more like a short form or like a condensed form. But if we completely spread out the S block, as you see here, we have the S block and the D and P. We saw that our inner transition metals, the F block elements, they were squeezed inside the D block. So what we have basically done is that we have stretched the whole thing and showing you the long form of the periodic table. And in the S block, you can basically see 2 columns. And in the P block, you can see you have 6 columns. So they kind of reflect the number of electrons they can hold in a particular orbital. You know, in S orbital, there is only one type of orbital, and each orbital can hold a maximum of 2 electrons. So for S, you have 2 columns. For P, you know, you have 3 p orbitals, each orbital holding a maximum of 2 electrons. So the maximum number is 6 electrons for the p orbitals, and that kind of reflect here 6 columns in the p block. And in the case of d block, you remember for d orbitals, you have 5 orbitals, each orbital holding a maximum of 2 electrons, and 2 electrons per 5 orbitals, you end up with the total of 10 electrons, reflecting 10 columns for the d block, one left here. And then for the f block, remember for the f, we have 7 orbitals. Each orbital can hold maximum of 2 electrons, leading to a complete 14 electrons. So if you count, you will find 14 columns for the f block. So the number of electrons kind of is reflected from the number of columns we have in this periodic table. Now, once we have set up this periodic table, we can see certain trends. Now, this is like the long form, but when we have this modern periodic table, we can figure out certain trends in these elements. And we can actually see the properties of these elements are dependent on the electron configuration. Basically, we can explain certain properties of the elements by looking at their electron configurations. Now, I'm going to show something which is actually not in your syllabus of chemistry, but it will be in physics. So I'm not going into details of physics, but let's just take 2 charges. Let's say we have a positive charge and a negative charge. You know from your general sciences that opposite charges, they're going to attract. So the attraction, there is some sort of an attractive force. So you have an attractive force. And this attractive force, if not, I'll just call it force, is actually proportional to the magnitude of the charge. What that means is that if you consider 1 plus charge and a 1 minus charge attracting towards each other with respect to a 2 plus charge and a 2 minus charge. Now, the force associated in the second situation, this force can be much more stronger. This is the force 1. This is the force 2. So if we consider the magnitude of charge, we can say that the force 1 is smaller than the force 2. The force 2 is much more stronger because the magnitude of the charge is much more larger than in the first couple of charges. And then I'm going to take another 2 charges. Again, I have a plus charge and a minus charge. Now there is a certain distance between these two charges. I would call it as the D1. And I'm going to take another two charges. This time, I'm going to place them far away from each other. Now, this new distance is D2. This is the distance. The distance between two charges. Now, you can see that the first distance is smaller than the second distance. The second distance is much more larger. All right. So if you try to build another relationship between the force and the distance, in which way will this distance affect you? When the distance increases, you will see that the electrostatic force, the attractive force, is going to decrease. So the force is inversely proportional to the distance. The force is directly proportional to the magnitude of the charge, but the force is inversely proportional to the distance. Now I'm going to plug in some symbols. For the force, I would just use F, and the magnitude of the charge, I would just use Q. I would call this as the Q1 and the other one as the Q2. And for the distance, I have the symbol D. Now I know that force is proportional to the magnitude of the first charge and also the magnitude of the second charge. It is direct proportionality. And the force is inversely proportional to the distance between the distance the Q1 have from Q2. So this distance from Q1 to Q2, I have a distance of D, which is an inverse proportionality. And then from Q2 to Q1, I have another D, the same distance. So like this. And then I can rewrite my equation as Q1, Q2, D squared. Now this is a proportionality sign, which is a pain to work with this. We can put a constant to get rid of the proportionality sign. I would put a K, Q1, Q2, divided by D squared. Now this is what we call as the Coulombs flow, which you will come across in one of your physics lessons. Unfortunately, that physics lesson does not line up perfectly with this chemistry lesson in the syllabus. So you may not see the relationship between that physics lesson and this chemistry lesson we are going to do. So that's why I'm bringing this up at this point. So next time you're learning your physics lesson about the charges, you will be doing a lot of calculations with these things. Think about the topic that we are going to do with this concept. We are going to talk about something called effective nuclear charge. So this Coulombs flow is applicable in this topic of effective nuclear charge. So you will go in the, greater detail in the physics, but what we need to know is these 2 points. The attractive force, the force is proportional to the magnitude of the charge, and also it is inversely related to the distance. Now, how does this fit into our chemistry lesson? Think about atom. In the atom, if this is our nucleus, in the nucleus, we have our positive charges. And then we learned about our quantum numbers and the energy levels. We know we have energy levels like this. And in these energy levels, we have our electrons. In the first level, we know that we can have a maximum of 2 electrons in the first energy level. And the second energy level, you can recall writing the electron configurations. I just write around 1s2, 2s2, 2p6. So this is the first level. You can see maximum of 2 electrons. And here you can see the second energy level. What is the maximum number of electrons? You see here, that is 8 electrons. So now you can find the other electrons in the outermost shell. Since I have drawn only 3 protons here, I would put just 3 electrons. So these are my 3 protons and 3 electrons. Now let's think about this Coulombs law we wrote here. We have charges. We have distances. How is that related? We have charges, the protons positive charge, electrons negative charge, and with the increasing energy levels, we have changing distances. So let's think about how this force is going to work. If you consider the nucleus and the electrons in the first energy level, there is, let's call this D1. And the next distance as the D2. We have our energy level. This is n equals 1, and this is n equals 2. What do you think about the distance? How do you think these electrons are feeling the nucleus? So if you think about electron in n equals 1, will have strong attraction towards nucleus. Why? You have a smaller distance. Between the charges, between the opposite charges. And the electrons in n equals 2 have less attraction. The reason is large distance. Now try to understand this inverse relationship. Distance in this equation is a denominator. So what does that mean when you get a larger denominator? let's say 1/100 versus 1/10. Now, here we have 10 as a smaller denominator and 100 as the larger denominator. In the case we have a larger denominator, our actual number is much more smaller. So if you have a large denominator, you end up with a small answer. If you have a small denominator, you will have a larger answer or a larger numerical value. Same here, you have a smaller d. If you have the smaller d, you have a stronger attraction. And when you have a larger d, you have a weaker attraction. So that means as you go to higher quantum numbers, higher principal quantum numbers, the electrons are less tightly attracted or attached to the nucleus. So the take-home message from all these is that as the principal quantum number increase, the electrons are less tightly attached. And it is not just the distance that we talked earlier. It is not just the distance. Distance is one factor, and the other factor is the magnitude of the charge. So, factors affecting the force. One, it's distance. When the distance increase, the force is going to decrease. And the second factor is the magnitude of charge. When the charge increase, the force is going to increase. Let's take two examples. Let's take hydrogen versus helium. In hydrogen, you have only one proton, and you have the n equal 1 level. And in the case of helium, you have two protons, but you still have the n equals 1. So let's take the electron in hydrogen and the electrons in helium. The attractive force, this attractive force, if I call it F1, and this attractive force between helium electron and the nucleus, we can say that F1 and F2, F2 is stronger than F1, the force 1. Why? Because helium has a larger magnitude in the nucleus. In the nucleus, it has a 2+ charge. So it has a stronger nuclear charge that will more strongly hold the electrons of helium. It is another reason why helium is an inert gas. It is very less reactive. It's not just the electron configuration where it has completely filled 1s2 orbital. It's not just that. Even thinking about Coulombs law, the nucleus doesn't want the electrons go because there is a stronger attractive force. All right. Now, this is a little bit simple if you're talking about hydrogen and helium. You can easily think about the attraction between the electron and the nucleus. But things can get slightly complicated as you go on into other elements that has more energy levels. So let's look at some other examples. Let's take lithium, for example. Lithium has the atomic number 3. So if I am to draw this atom, I have 3 plus charges in the nucleus. I have my first energy level, which is n equals 1. And then I have my next energy level, which is n equals 2. And I have my first 2 electrons like that. And I'll put my third electron somewhere there. Now, in this case, you can see that you have attractive forces between the nucleus and the electrons. But in addition to that, we are going to have, so I will write attractive forces between nucleus and electrons. So we have that attractive force. But there is another force working on, that is the repulsions, the electrons and the electrons. We know that electrons, they are of the same charge, negative charge. Similar charges, they repel each other. So in addition to the attractive forces, now there are repulsive forces. Between electrons. So this repulsion can get bigger and bigger as you keep on adding more electrons. Now we did the periodic table. What is the element right below lithium? If you check the periodic table right below lithium, you will find sodium. Sodium has the atomic number 11. So that means it is going to have 11 plus charges in the nucleus. And then sodium is in the third row, meaning it is going to have 3 levels. So this is n equals 1, n equals 2, and n equals 3. It will have its first 2 electrons and then eight electrons. So 8 plus 2, that is 10. I have atomic number 11. So the neutral atom. I have my last electron outside here. Now think about the attraction between this last electron in n equals 3. What kind of a force will this electron feel between that electron and the nucleus? Do you think this yellow colored electron in the last shell will feel the nucleus strongly? No, it cannot. There are lots of repulsions going on. This yellow electron in the outermost shell is repelled by these electrons. All these electrons are repelling the outermost electron. So this yellow marked electron here, it experiences a strong repulsion from inner electrons. So because of that, this outermost electron is less tightly attached to the nucleus. So this electron, the outermost electron, feel the nucleus less strongly. What about the other electrons inside? Like if you think about this electron in N1, this can feel the nucleus very strongly. This is strongly attracted to nucleus. But the yellow mark one is weakly attracted. We actually don't use the word weakly. We instead say less strongly, comparatively less attraction. So now you see, in addition to the attractive forces, as we keep on adding more and more electrons, there are some internal repulsions. Now, if you want to visualize this in a bigger scale, think it like this. Think like this milk bowl is the nucleus, and this first cat is like the inner shell electrons. So the inner shell electrons are actually pushing away the outermost electrons, which we are calling as the valence shell. So this yellow one, you can see it's in the outermost shell, the outermost level. And this electron is being pushed away by all the inner electrons. So the outermost one is less attracted towards the nucleus. In other words, it is loosely held. So that is why it is easier in the chemical reactions to use the valence electrons in a reaction. We say in a chemical reaction, valence electrons participate. The reason valence electrons can participate is that they are less tightly attached. They can be donated. They can be shared because they are not very strongly held by the nucleus. Now, why we were looking at all these concepts is because we want to go and talk about another topic, which is effective nuclear charge. So because of this repulsion experienced by outermost electron, this outermost electron doesn't feel the full attraction of the nucleus. Instead, what it feels is something called a net attraction, which we call as the effective nuclear charge. So this attraction felt by the outermost electron. This is not the full nuclear charge. So it is more like it feels a partial charge. What I mean by it, the electron. So let me correct it. The outermost electron feels a partial charge, not a full charge. So this partial charge is something we call as the effective nuclear charge. Also showing by the symbol of Z effective, or you can call it as Z. So in short, effective nuclear charge is not a full charge felt by the outermost electron. It is a partial charge. It feels a partial charge because of the net effect of the attractive and the repulsive forces. So at the end, what this all means is that as you keep on adding more core electrons or more shells, your outermost electrons feel less nuclear force. So compared to having one shell and two shells, or having even more shells. As you keep on going, the electrons outside, these electrons keep on feel less nuclear charge. It feels less nuclear charge because the core electrons feel less nuclear charge because the core or the inner electrons shields the inner electrons are going to shield the nucleus. Which we call as the shielding effect. So the reason why the valence electrons, I would write valence electrons feel less nuclear charge because the core electrons or the inner electrons covers the nucleus. It covers the nucleus and also cause some repulsions so that the outermost electron or the valence electron is going to feel the nucleus less strongly. Now, if you think about this Z I just mentioned, or the effective nuclear charge, and the actual nuclear charge. What do you think is larger, the actual nuclear charge or the effective nuclear charge? It should be the actual nuclear charge. The actual nuclear charge is larger than the effective nuclear charge. The effective nuclear charge is smaller because of the shielding effect. Shielding effect is basically the core electrons covering up the nucleus so that the valence electrons are going to fill the nucleus less tightly. Now let's look into this shielding effect and the effective nuclear charge a little bit more. If we consider hydrogen, for hydrogen, we have only N equals 1. And think about lithium. We have N equals 1 and N equals 2. And now we have lithium 2 electrons here and the third one out here. So you can see this last electron, the outermost electron, feel less nuclear charge due to the outermost electrons. If we go a little bit down, the next level, you have level 1, 2, and 3. You can see how this keeps on getting larger and larger. And as you go down, you keep on adding more N levels. N is the principal quantum number. So you can see a certain size. The size of the atom kind of keep on increasing because you keep on adding N levels. And as you keep on adding N levels, you are adding more core electrons, more inner electrons. So the more inner electrons you have as you go down from top to bottom, what do you think is happening to the shielding? The shielding as you go from top to bottom should increase, because you keep on adding more core electron. And then we talked about the effective nuclear charge. Let's think what is happening when you go across the period left to right. Let's consider hydrogen and helium. In the helium, I mentioned that they have the same N level, but you keep on increasing the number of electrons, and also at the same time, you increase the number of protons. What happens as you go from left to right? When you go from left to right, you increase the atomic number. When you go from left to right, you increase atomic number. In other words, it means that you are increasing the number of protons in the nucleus. Increase the number of protons in nucleus. And in other words, it means the magnitude of charge increase. the magnitude of charge in the nucleus increase. Now remember the Coulombs law. What happened to the Coulombs law when you increase the magnitude? The force increase. So when you increase the magnitude of the charge, your force increase. And what else happened is that even though you're adding more electrons and more protons, you're adding the electrons to the same level. For hydrogen, you had n equals 1, and you added the second electron. When you go from hydrogen to helium, your atomic number increased by 1. So you have one more positive charge. In order to neutralize that additional positive charge, you need an additional electron. So the second electron also adds to the same level. So basically, in this Coulombs law equation, your D doesn't change because you're adding things into the same level. So your D doesn't change, but your Q increase. So that means your force increase. What does that mean? Going from left to right in the periodic table, your Ceph increase. Why? The Ceph increase because the nuclear charge increase, and electron adds to the same end level. So the distance doesn't change. Think about lithium, beryllium, boron, carbon. They are all in the second period. So if you think about the electron configuration, this is 2s1, 2s2. And come to boron, that is 2s1, 2p1. So you see the principal quantum number. We are still in 2. You keep on adding electron into the same level. The orbital can be different. When you come to boron, you're adding the third electron. This is 2s2, 2s2, 2p1. So you're adding the third electron to the p orbital, but that p orbital is still in level 2. So you're not increasing the level. So that is why going from left to right in the periodic table, your Ceph increase. Now this is something we can call as a periodic trend. Going from in a certain direction, either from top to bottom or left to right. So periodic trends. We got the periodic table by organizing the elements in their increasing order of atomic numbers. And now we see this kind of trends. Your Ceph, the effective nuclear charge increase from left to right, and your shielding increases from top to bottom. So considering of the trend going from top to bottom, I mentioned that shielding increase going from top to bottom. If the shielding increases, what do you think should happen to the Ceph? If the shielding increase, this outermost electron feels less nuclear charge. So as a result of increasing shielding from top to bottom, you can see that from top to bottom, the Ceph decrease. Going from top to bottom. a periodic trend. Going from top to bottom, your shielding increase. As a result of shielding increase, your effective nuclear charge will decrease. But what will happen in the trend from left to right? From left to right, we mentioned that your ZEF is increasing. Your ZEF increase because your nuclear charge increase. You keep on adding more proton, but you keep on adding electrons to the same level. So do you think shielding is going to change across the period? Would you expect the shielding to change? No, there isn't much change. So going from left to right, shielding stays pretty much constant. Shielding is more or less constant. Why that happens? You don't add more levels. Going in the same period, you are not adding more energy level. Instead, you're adding electrons to the same energy level. Let's take a look of what I said. Now I'm going to erase this extra stuff just to make things a little bit clear. So let's take this lithium atom. In the lithium, you have the level 1 and level 2. Next, let's take beryllium. For the beryllium, I have level 1 and the level 2. I have 4 electrons. From the 4 electrons, I have 2 electrons here, and the other 2 goes to the outer shell. And then I'm going for my next element, which is boron. Still in level 2. So I have level 1 and level 2. I have my 2 electrons here, and I should have the other electrons in the outer shell. So 1, 2, 3. So as I go on, I can do carbon. If I do carbon, for this, I have my nucleus, the level 1 and the level 2. You can see I have this kind. So what is my inner shell? What is my inner shell? This is my inner shell, or the core. This is my inner shell. This is the inner shell. Did the number of electrons change in the inner shell? No. In every element, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, in all of them, I have only 2 inner electrons, or 2 core electrons. So my number of core electrons didn't change. So that is why my shielding is constant. The shielding is constant because the number of core electrons did not change. Okay, now in the periodic table, we are going to look into a lot more trends. But these 2 trends we talked about right now, ZEF, the effective nuclear charge, and shielding, can explain most of the trends you see in the periodic table. So the other trends, like it's like the Holy Grail. ZEF and shielding is like the holy grail for predicting all the other periodic trends. And next, what we are going to do is see the other periodic trends and see how the ZEF and shielding can affect the other periodic trends. So let's move on and see how the other trends can work. So just to sum up, in the periodic table, from left to right, your ZEF increase, and from top to bottom, your shielding. The shielding increase. And due to shielding increase, as a result, ZEF decrease. All right. Now, we are going to talk about something called the size of the atom. For the size of the atom, when we were initially talking about atoms, we kind of visualized atom as a spherical object, a tiny spherical object. And if you think about a spherical object like a ball, it has a fine boundary. But the issue is in a thing like an atom, because we are using quantum model, we cannot define a fine boundary. So for the atom has no sharp boundaries. So in quantum model, this is according to quantum model. So in the quantum model, we are actually talking about the probability of finding an electron in a given place. So it is more like a distribution map. So because of that, we don't have sharp boundaries. It's more like a cloud-like structure. So in that kind of a structure, how can you define size? Now we have an issue of defining size. If we have no sharp boundary, how can we measure a size? Because of this issue, we are going to define the size of atom in different ways. Because atom has no sharp boundary, we have an issue in defining size. So we are making this atomic size in different methods. Atomic size can be given by different methods. Because the atom has no sharp boundary. So the size of atom or the ion can be given one way by van der Waals radius. So van der Waals radius is one way of defining the size of atom or ion. So what is this van der Waals radius? This is also known as the non-bonding atomic radius. Now the word says it, non-bonding. There is no bond formed. Think about an atom like this, and this is the first atom of one element, and take another atom from the same element, atom 2 from same element. Keep the atom 1 still and bring the second atom towards the first atom. You bring it closer in a way that you have your first atom like this, and your second atom is close enough so the second atom is close enough, there is maximum attraction between two atoms. But don't make a bond. So the key things is that you have two atoms from the same elements. You bring them closer until they have the maximum attraction, but they don't make a bond. In this kind of a situation, if you measure the distance between these two atoms, this D, and divide it by 2, half of that distance is what we call as the van der Waals radius. As the word says, non-bonding. Bring the two atoms together, you don't make a bond. Measure the distance between the two atoms, divide it by 2. That is your van der Waals radius. And there is another way to measure the size of the atom. The first way is the van der Waals radius. The second way is what we call as the covalent radius. Now here you can see the two atoms has been brought close enough that they are going to have maximum attraction, but there is no actual bond formation. So this gap here indicate that there is no bond formation, but they're experiencing the maximum attraction without making a bond. The second way we can define a size for atom is by the covalent radius. The covalent radius is also known as the bonding atomic radius. Now, in the previous one, here I have shown you the van der Waals radius. You can see there is no bond formation indicating this tiny space inside. But in the second one, I'm showing you the covalent or the bonding. Van der Waals was the non-bonding. you can see that these electron clouds are kind of overlapped. They are overlapped, there is maximum attraction, and there is a bond formation. In the van der Waals, there was no bond formation, but in covalent, there is bond formation. So there is bond formation. Now take this distance and divide it by 2. That is your covalent radius. Now, what do you think when you compare the covalent radius and the van der Waals radius? Which one should be larger? The van der Waals radius is larger because in the van der Waals radius, you don't have a bond formation or the overlap of the electron cloud. Now, this is the second type of way we can define a size for the atom. Another way we can define the size for an atom is the metallic radius. This metallic radius is defined for metal atoms in the metal structure. This is defined for metal atoms. So the metal atoms in a metallic structure, they are bounded by metallic bond. Now let's compare this van der Waals bond with the covalent bond. This is van der Waals. And the second one is covalent. And the third one, metallic radius. In the van der Waals one, you see that it is not bonding. It's a non-bonding. Covalent, it is bonding. In the metallic, it is also a type of bond, but there is a small difference. It is not like very tightly overlapped covalent bond. It is not exactly like the overlap you see in covalent bond. So in the case of metallic radii, again, we take this distance between the two atoms and take half of that distance. So that is what we define as the metallic bond or the metallic radius. So we have to use these 3 types of radii because the atom does not have a fine boundary. There is no sharp boundary. Now, since we talked about the atomic size, these atomic radii, now let's try to fit that into the periodic table and see the trend. So let's see the atomic size or the radii as a periodic trend. what kind of a trend do you see? You can see that when you go from left to right, your size of the atom shrinks. So going from left to right, either you can say the size of the radius decrease, or going from right to left, the atomic radius increases. And what kind of a trend do you see going from top to bottom? Going from top to bottom, you can see that the size of the atom increase. Now, do you think you can relate these things with the previously discussed concept, the effective nuclear charge and shielding? What did you see in terms of ZEF from left to right? From left to right, effective nuclear charge increase. What it means is that outermost electrons feel the nuclear more strongly. Outermost electrons feel nucleus strongly. So what happened is that the nucleus is like, it's like sucking in the outermost electrons. From left to right, ZEF increases and shielding is constant. Shielding does not change. So what happens is the effective nuclear charge increase as we keep on adding protons going from left to right in the periodic table. So as a result, ZEF increase, the outermost electron feels a stronger nuclear force, nuclear attraction. So it's very tightly held, like it's like sucked inside. So that's why you can see a shrinking of atomic size going from left to right. But in the case of going from top to bottom, what happened is that you saw shielding increase. Shielding increase, and you keep on adding more N levels. So as you add more N levels and as you have increasing shielding, the size of the atom increase going from top to bottom. So the size of atom increase from top to bottom, you add more N levels, your shielding increase, but across the period, your size shrink because effective nuclear charge is increasing. So now you see how this trend of atomic size can be explained by effective nuclear charge and shielding. So don't try to blindly memorize the trends. You are required to know these trends in the periodic table, but don't try to memorize it, but rather understanding. The driving force is ZEF and shielding. Because of the ZEF and shielding, you saw this trend in the atomic size. Okay, so our next topic is actually the electron configurations of ions. So I want to talk about the electron configurations. But I don't think I have enough time to go over the whole concept. So I will be doing it in the next session.